Hello, welcome to the Advanced Undergraduate, Intermediate, Graduate series on Calculus of Variations. Today's topic is a continuation of Euler-Lagrange equations, designation CV03, and the difference between this and the previous lecture is that I'm going to consider functionals that have also got second derivatives in the independent variable. So let's just define the problem. This looks very much alike like the previous one. So we're going to have a functional j of y, where y here is a vector valued function, so it has many different components, y1 through yn, each of which are functions of time. The Lagrangian here, which defines the functional, has arguments in y, arguments in y dot, and arguments in y double dot. So if this was a scalar, that would be it. If y was a vector, then this y dot here represents the time derivatives of each and every component that might define L. The underlying vector space is that the function y maps from a to b to Rn, and the yi's are C4, or 4 times continuously differentiable on the interval AB. I'm not really going to explain why that's the case. Why would I do C4? But in the example that I'll be giving later, it'll become quite apparent that you need some sort of smoothness up to 4th degree. Okay, we're going to look at this functional on an admissible set. The admissible set will be all the y's in that vector space that are at t equal a and t equal b. They are pegged at endpoints. So this a here is actually a vector. B here is a vector 2 for all the components of y. But in addition, we're now going to stipulate that the t derivatives of y at the endpoints are fixed as well. It is actually somewhat arbitrary how you define a. It just depends on what type of problem you're looking at. We're just going to look at this kind of a problem, and there's a real world example which pertains to it. So if that is the admissible set, then we need to understand what the admissible variations of that are. And basically, it's fairly easy to see that the admissible variation should be the etas in that vector space that are 0 on each and every one of the boundary conditions above an A. Why is that? Because I want to be able to take a y out of the set A and add epsilon times eta and still be in the set A, because I'm going to be comparing these sums. So down here, I'm wanting this statement to be true for all epsilons if I fix an eta. And by doing that, we can define the first variation. So it's pretty clear that if, in particular, if eta dot on the boundaries are 0, then when I take an 8 out of here and I add it to a y, I still get a sum that's in the set A. Like all of these problems, we need to consider the value of the functional at slightly different from a fixed y. So I want to compute the first Gateau variation of this functional. And the way we do that is we evaluate the functional at y plus epsilon eta. We fix y, and we're fixing eta, and that gives us a function of epsilon, which epsilon is a real number. So in each of the arguments of the Lagrangian, I substitute that sum. So the first argument will be the y's. The second argument will be derivatives of the y's in t. The third argument will be the derivatives of y in double derivatives in y in t. And then there might be a t that sits along with it. So I have to look at this integral here, and what I'm going to do is I need to find the derivative of that integral in epsilon. And when I'm done with that, set epsilon equals 0, and that will mean evaluating everything at simply at y and not the sum. So I need this delta j first Gaussian variation to vanish for all the etas in the admissible set A star. Okay, how do we do that? Again, I'm going to take the epsilon derivative of this integral that I'm highlighting up here, and I'm fixing y and I'm fixing eta, and I'm taking the derivative in epsilon. So when I take the derivative on the outside, it becomes a partial derivative of epsilon on the inside. And then if I'm taking partial derivatives on the inside, I've got 1, 2, 3 arguments that have epsilons in them. So there's going to be a chain rule for each and every one of those arguments. And then when I'm done, I'll set epsilon equals 0. So it's pretty clear to see that when I do that, I get the following expression down below here. Basically, the derivatives in all the y components times eta I, derivatives of L in all the y I dot components times the eta I dot, and then the derivative of L in the yi double dot arguments times the respective eta I double dot. As before, we're using the Einstein notation, double sum notation. This expression here, if you see a repeated index, it means a sum. So this would be a partial of L in y1 times eta 1 plus partial of L in y2 times eta 2, etc. So we have an expression for the first variation, but it's not the one that we need to find the Euler-Lagrange equations. What we need to do there is we want to make this integrand look different in the following way. I don't want to have derivatives of eta in this expression. So there's an eta I dot here, and there's a eta I double dot there. I can get rid of the dots by doing integration by parts on this one here. So if I do integrate by parts once, the derivative on this will go down by 1. To make that happen for the second term here, this eta double dot, I need to do 2 integration by parts in succession. So if I simply do that, I do these multiple integration by parts, what do I get? I get a boundary term plus an integral of an expression times eta I. And again, this is a sum of eta I. So it's a parentheses times eta I dt, and that's the sum. This boundary term those are all the terms that you get by doing integration by parts, and they're evaluated at t equal a and t equals b. And in fact, if you collect them, if you look at them and you do that, you find that the terms that multiply eta i's is this expression here. And the terms that multiply eta I dot is this partial of L in yi double dot. Now, as I get to the next slide, when I look at this boundary term, we remember that these etas here, that eta there, and this eta I dot here, those have to be in the admissible set A star. Any single eta in that set. Every eta in that set has these eta i's vanishing on the boundaries. What that means is that if I choose an eta in the admissible variation set, this entire term becomes 0. So that's my next statement. I say it up here again. Since eta is in the admissible variation set, the eta i's of t and eta I dot of t vanish at both the endpoints, meaning t equals a and b. That implies the boundary term is 0. Rewriting that delta j first variation, then, it becomes an integral of something times eta I. This statement this whole expression here must vanish for all etas that are in particular continuous on the interval AB. And as per our previous discussion, if you have some fixed function times a function that is continuous, and you say that this fixed function integrated against an arbitrary continuous function is 0, then you can conclude that the term in the parentheses is equal to 0. That's this fact I talked about last time, if it's an analysis fact. So, what does that mean? It means the only way that this whole term can vanish for every single eta is if each and every one of these terms in the parentheses vanish. So let's state that as a theorem. If the Lagrangian here is C2 in its arguments, we don't need to see exactly why that is, but basically I want to be able to take derivatives in this part here. But so if it's that smooth and y of t in A extremizes the j, then the necessary condition is that the y of t in this set satisfies this new Euler-Lagrange equation. It's actually equations because the y's may have many components. They may have one component, which is the example I'm going to give. They may have many components. But to compare and contrast to the last lecture, the Euler-Lagrange equation from the last lecture is actually these first two terms is equal to 0. That is to say that if there is no y double dot in Lagrangian, if there is no y double dot in there, then this partial derivative will go away, and you'll be left with our old Euler-Lagrange equations. But if there is a second derivative in L of the dependent variables yi, then this term will be non-trivial. And so you've changed the Euler-Lagrange equations, and but you still have a new necessary condition for the extrema. So this before I do an example, this highlights the following fact. If when you change the Lagrangian, you'll get different Euler-Lagrange equations. So when someone says, oh, the Euler-Lagrange equation, it's really not one equation, it's many, and it depends on what the Lagrangian is. So there's a Euler-Lagrange equation or equations for each and every kind of L. Okay, so let's see what this particular kind of functional dependence can be used for. This is the standard example for this kind of problem. It's an elastic beam problem. Here, up above here, very, very simple. So the thing in black is a beam, and it's sagging in the middle, and there's a couple of factors that are going on with an elastic beam. The beam is assumed to have certain kinds of linear elastic properties, like a spring, and so it has some sort of tension in it as a result of the elasticity. But the weight of the beam itself is enough to bring it down. So you'll have if you just put a beam, it won't necessarily be straight across, it'll sag a little bit, and that due to the weight. You could also have things that are being put on top of the beam, and that's considered to be a load. So perhaps I could put sand in various amounts along here that change the amount of mass at a particular x that's being exerted on the beam. So as simple as this drawing is, there's still quite a lot of variation. One other thing about this problem that's specific to our analysis in the previous slides is that the derivative of the y at the endpoint is 0. That means this curve has to come in flat at this boundary here. And that would be true if this beam, let's say the way that you secured it to the wall, suppose you put a flat part of it inside at a level as I'm trying to draw right here. It's like something level, and it comes out of there. So it's got zero slope, and then it starts to change shape. So that's called, that particular case is a case of a beam which has no moments at the boundary. Why am I making a big deal? We'll see this later, but you could have had this beam connected to a pin, and there could be a rotation at this endpoint because it's connected to a pin and not actually to the wall. And in that case, the derivative need not vanish. But we'll come to that later. But for now, we're just going to consider this type of beam that has zero slope at both boundaries. So it means the boundary conditions for this y of x is exactly what I'm talking about. Y is fixed at both boundaries to be 0, and y prime is fixed to be 0 at both boundaries. So there's some theory in elasticity theory concerning all this problem, and the theory is physics. It has its own assumptions. It's not really something that you derive per se. At some point, physics just is a set of assumptions. And for linear elasticity theory, there are well-developed notions of potential energy due to the elastic nature of the object. I mean, if you take a spring, for example, and you pull it, you get 1/2 kx squared is the potential energy in an extended spring. So there's squares of second derivatives that are going to be involved in the stretching part of this. But we won't go into that whole discussion. We're just going to say we trust these people, and we're going to look at how they compute the total potential energy. The total potential energy of this shape depends on how deep it goes and how much tension there is in the beam, and the beam itself has got a property called the flexible rigidity, and that's going to somehow affect exactly what the potential energy, the elastic potential energy. So here we go. So what we have in this, the theory basically says that if I know the beam shape, then the total net potential energy of that beam depends on a part that contributes, which is the elastic potential energy, which is this thing in blue, minus a load potential energy, or just simply the potential energy due to the weight of the beam. So this thing here could depend on x. So there could be there could be a load distribution, or it could be that this is just simply constant. This P here has got units of newtons per meter. So when you look at this, it's like newtons per meter times meters gives you newtons. So the P of x dx is the force times the distance y gives you work done or potential energy. So the functional here, we won't, again, this blue thing, we're going to accept it. So the total potential energy, J of y, is given by this double integral, which has a second derivative, and the second derivative is proportionate to the curvature of the object. So more curvature there is, the more elastic potential energy there is. And as I said before, so our set it fits in here down here. This is our admissible set. The beam is fixed at both endpoints at 0, and it has no moment at both ends. So that means the derivatives are also 0. And when you look at A star, the admissible variations is going to be exactly equal to A. So it's not only a subspace, A and A star are the same. Okay, here's how we solve this problem. We're looking at an L elastic. We have an elastic potential Lagrangian up here highlighted in blue now. And I want to just use this L in the Euler-Lagrange equation. So what do I need to compute? I need to compute the partial of L in y, partial of L in y prime, partial of L in y double prime. Partial of L in y, if I look at this, the only occurrence of y is over here. So I take the partial of that in y and I just get minus p. So here we go, my L sub y is minus p. Go back to L. What is the partial of this thing in y prime? There is no y prime in there, so when I take the partial, it's 0. What's the partial of this thing in y double prime? Well, it'll be 2 times the half mu y double prime. That would be this. So now, so this Ly is minus p, this thing is 0, and this second term is the second derivative of what? Of this. Well, mu's a constant here, so the second derivative of this expression is the mu times the fourth derivative in x. So this is where the fourth, my discussions earlier about what kind of smoothness do you need? You need the y's to be C4 so that this differential equation makes sense and can be solved and gives you something with relatively smooth properties. So to recap, if L is this, if this Lagrangian has this expression, the Euler-Lagrange equations that must be satisfied by the extrema is this expression in blue. We just derived it. So what is that? That is a fourth order differential equation, and it's a very simple one. The way that we solve it is we merely integrate both sides 4 times. When you do that, you can find out what, in particular, about mu times y of x is. It's just integrate the right side in x 4 times. And we're going to presume here that, let's say, mu of x is constant. And so you know what that means. So that could be, for instance, the case that it's a beam that has the same lineal density all the way along. So the load per unit length is going to be p, a constant. So in that case, I can integrate this thing 4 times and I get this expression here where I have C1, C2, C3, C4, all arbitrary constants. Why is that? Oh, if you go backwards, if you think about this, if I differentiate all these things that have got arbitrary constants in it, if I differentiate it 4 times, that cubic, the derivative of the cubic, the fourth derivative of any cubic is 0. So C1 through C4 doesn't matter. It'll still satisfy that. But the actual minimizer, y of x here, so it has to have this form to satisfy the Euler-Lagrange equation. But the constants of integration are determined by the boundary conditions defining the admissible set A. In particular, y of 0. If I look at that, that says C4 is 0. If I do the derivative of this in x and then say x equals 0, I get C3 is 0. So in other words, derivative in x would be, derivative of C4 in x would be 0. Derivative of this term in x would be just C3. Derivative of any one of these other ones at x equals 0 will vanish. So y prime of 0 is 0. You do the same, y of 1. If I put x equal to 1 in here, the length, 1, 1, 1, 1, 1, I get p over 24 plus all of these constants equal to 0. And I do the same kind of thing with the first derivative at 1, and I get this. So what do we have? We actually have 4 equations for 4 unknowns. The 4 boundary conditions determine the 4 unknown constants of integration. The logistics here are not too complicated. If you look at this, well, C3 and C4 are 0. So if you look at this third equation, this term that I'm highlighting is 0. And if I look at the last equation, this term that I'm highlighting is 0. What's left is two equations for two unknowns, C1 and C2. It's a linear system. I solve it, and I find out what C1 and C2 are. Once I find out what C1 and C2, I put them back in here, here, and here, and then noting that this term is gone because C3 and 4 are 0. And I've got an expression in powers of x squared, and I just do a little bit of simplification, and I discover that the y of x that satisfies this Euler-Lagrange equation with the 4 boundary conditions must be the following thing in that I'm highlighting at the bottom. That gives you a formula for the shape of the beam that minimizes the total potential energy. So that's a very real-world practical example of where these second derivative of the dependent variable comes into the Lagrangian. That's the only example I'm giving for this Lagrangian case.